Hello, in this video we're going to continue looking at momentum as well as force and impulse. So momentum may be transferred from one object to another when a force acts over a time interval. The rate of change of momentum of an object with respect to time is equal to the net force acting upon the object. This can be expressed mathematically as force is equal to the change in momentum divided by the change in time. The impulse of an object is equal to force times the change in time, and consequently, or is also equal to the change in momentum. In stage 1 physics, you need to be able to use Newton's second law of motion in the form of force equals mass times acceleration. Hopefully you're familiar with this. So you need to be able to use this to derive the formula that we have here. You also need to be able to solve problems involving changes in momentum and impulse for one dimension, and you'll need to be able to draw and interpret graphs of force versus time. So looking at rates of change of momentum, we know from Newton's second law of motion that force equals mass times acceleration. We also know from our motion work that acceleration is equal to the change in velocity divided by the change in time. So we can use these equations here to derive this equation here, so force equals change in momentum over time. So I'm going to go from F equals mass times acceleration to F equals mass times change in velocity divided by change in time. So this equation here, we're just subbing in that value or that equation for acceleration. Change in velocity is equal to the final velocity minus the initial velocity. So I can change or sub this in now to the equation that we have here. So mass times final velocity minus initial velocity divided by the change in time. Because our mass is out there, it's multiplying both this velocity and this velocity, so the final velocity and the initial velocity. So if we were to expand this, we'd get m, or mass times velocity final, minus mass times velocity initial, and that would all be over change in time. We know that momentum is equal to mass times velocity. So, oops, missing my vector signs. This here is going to be the final velocity, the final momentum, because it's the final velocity, and this here is going to be the initial velocity because it's got the initial acceleration, the initial velocity. So overall, we'll have momentum final minus momentum initial over the change in time, and the change in momentum is equal to the final momentum minus the initial momentum. So we can just write this as change in momentum over change in time, and that's how you get to this equation here, or how you derive that equation. So this derivation illustrates that the rate of change of an object's momentum is proportional to the net force applied to the object. So the rate of change of in momentum, which is momentum or change in momentum divided by the change in time, that's proportional to the net force. If we were to keep the same momentum, but we were to increase the time over which that momentum changed. So momentum staying constant, we're increasing the time over which the momentum changes. That will mean that the force that acts will decrease. So if this term here increases, this overall fraction or this overall number is going to decrease because you're dividing by a larger number, and this will therefore mean that the overall force will decrease. Or the force will be reduced. This concept is utilised in crumple zones of cars. So in the event of a crash, crumple zones increase the time over which the car's change in momentum occurs, and that reduces the force that impacts passengers. Or another way of thinking about it is it reduces the energy that reaches like the passenger carriage of the car, and therefore the passengers and that carriage aren't absorbing as much energy. Rather, it's the crumple zones of the car that absorb the energy, and that helps prevent injury in crashes. So we've got a 170 gram billiard ball at rest, and it's struck with a cue and moves horizontally with a velocity of 11 meters per second. We have to find what the change in momentum is. So change in momentum is equal to the final momentum minus the initial momentum, and that is equal to the mass of the billiard ball times the final velocity of the billiard ball, and then minus the mass of the billiard ball times the initial velocity of the ball. So 170 grams is equal to 170 by 10 to the negative 3, I've got no space here, kilograms, which is the unit of weight, the unit of mass that we use in physics, and we use 11 meters per second, so that's all good. So I'll put in the mass first, 170 by 10 to the negative 3 times the final velocity is 11 meters per second minus mass, and then times by the initial velocity, which is 0. Sorry, I've kind of crowded this part of the screen, but because this is times by 0, that whole term will cancel out. So we'll just be left with 170 times 10 to the negative 3 kilos times by 11, and that will be 1.87 kilogram meters per second. So our change in momentum is going to be 1.87 kilogram meters per second. If the cue is in contact with that should be ball, for 2 by 10 to the negative 3 seconds, what is the net force on the ball? To find the answer to this, we can use our force equals change in momentum over change in time rule. And we know that the time that the change in momentum occurs over, or that the cue is in contact with the ball for, is 2 by 10 to the negative 3 seconds, and our change in momentum is up here, 1.8 kilogram meters per second. So pop those in, 1.87 divided by 2 by 10 to the negative 3, and our resulting force, or the net force that was on the ball, is 935 newtons. So next what we'll look at is impulse, and this is represented by the symbol J for some reason. I'm not sure why I isn't used, but we'll just have to go with it. Impulse is force that acts over a time interval. So it's equivalent to the product of force by the change in time. It's also equivalent to the change in momentum, because if you think about force being equal to the change in momentum over the change in time, if you multiply both sides by the change in time will cancel out there, and you'll be left with momentum on one side is equal to force by the change in time. So given that impulse is equal to the force multiplied by the change in time, it's also equal to the change in momentum. Impulse is a vector quantity, so it has direction and magnitude. The unit can either be kilogram meters per second, which is the same as momentum, or you can use Newton seconds, because the unit for force is newtons, the unit for time is seconds, and these are being multiplied by each other. Impulse is also equivalent to the area underneath a force time graph. So if you think about this first example here, where a constant force is acting, we've got force on the y-axis here, and we've got time on the x-axis. So if you were to find the area under this graph, it's a rectangle, so you'd be multiplying the length by the width, and the length here is time, so you'd be timesing time by the width. The width is force, so you'd be timesing time by force. Our rule for impulse is, is force by the change in time, and that's exactly what you'd be finding if you were to multiply the length and the width of this rectangle. So the length of this rectangle, you can see here, is 20, and the width is 8. So 8 by 20, that would be 160 Newton seconds, and that's the area that we've gotten here. If you have a shape or a graph that is a bit more complicated than a straight line or a constant force, we've got a constant force to begin with, but then the force changes over time, then you just find the area underneath the graph by working out what shapes you can use to fill in the area under the graph. So you can just use your rectangle area formula here, because that would just be the length, which I guess in this situation is the force, and then the width would be the time. For your triangle, you'd use your triangle area formula, which is half base height, so it doesn't really matter which one if you use time or force as your base, because you're multiplying the entire thing by half anyway, so it doesn't matter what order you do it in, but just say area 2 would be equal to half base. We'll say that's, we'll say that's T, and then the height would be, T2, the height would be FO, and that would be the area of A2 here. Just for completion, I'll do area 1, which would be length by width, which would just be T1 FO. And then, sorry to jump all around this page, I'll just connect it over here. Your impulse, which is the total area underneath the graph, would be equal to A1 plus A2. Revisiting our crumple zone example, so crumple zones increasing the time over which a change in momentum occurs, and therefore decreasing the magnitude of the force it acts. The impulse is going to be the same regardless of the change in time as long as the corresponding change in force matches. What I mean by that is the overall change in momentum stays the same, so therefore the change in momentum, which is equivalent to impulse, will also stay the same. Coming back to our crumple zone example, so crumple zones increasing the time over which a car's change in momentum occurs if it's crashing. The impulse, which is equal to the change in momentum, stays the same. So the area underneath the force time graph stays the same. So here, just say this is a car without crumple zones, a large force acts for a short time. So impulse equals change in momentum, which equals force by change in time. So this is a really large force, it acts for a short time, and this change in momentum and therefore change of impulse stays the same. Here, so this graph here, or the shallower graph, this is still representing the same change in momentum and therefore the same impulse, because the area underneath both graphs are the same, but the overall force, or the peak force that acts, is only up to here as compared with up here for the blue graph. So the change in momentum is still the same, but the peak force that occurs is much lower. So in our crumple zones and our car that's crashed, the force experienced by the car and the passengers is going to be reduced, and therefore injuries that might occur as a result of the crash, the likelihood of that happening will be far less. The car itself will be cooked because the crumple zones have completely crumpled, but it's probably better that the car is cooked rather than the people inside the car. But the main point of this slide here is just to indicate that even if your force and time are altered, if the change in momentum is the same, the change in impulse is going to be the same. So if you're increasing the time over which change in momentum occurs, then the force will be less. So I thought we'd go through an example for this. So what is the impulse experienced by a 3 kilo mass subjected to the force described in the graph below? So we're just looking at impulse. So that means we just need to find the area under the graph. We've got negative areas here and here. So we will just add those negative areas. In other words, we'll subtract those areas because they're negative. So area is going to be equal to a bunch of triangles, half base height plus half base height plus half base height. The base of this first triangle is 2, and the base of this last triangle, so first one here, last one here, is also 2. So I'm going to fill those ones in, and then 2. The height of both of these ones is the same as well. It's negative 500. Oh, I hope I've left myself enough room. We shall see. And then of this big yoke here, the base of this one is 24686, and the height is 2000. Oh, let's see. Got it. So overall, this will be equal to 5,000, and our units for impulse are Newton seconds or kilogram meters per second. So the impulse experienced by the 3 kilo mass is 5,000 newton seconds or 5,000 kilogram meters per second. You don't always need every piece of information that's given to you in questions. So for example, this 3 kilo mass here, it's not required to find the impulse experienced by the mass. You just need to find the area underneath the graph, so that might have been a bit of a red herring to confuse. But if you know your stuff and if you know that you just need to find the area under the graph for impulse, you can just ignore that.